In section 6.4, we're going to look at general log and exponential functions here. So we want to look at things like y equals b to the x. And what we're going to do is we're going to define b to the x as e to the ln of b to the x. So by cancellation law, those are equivalent. And then this x, which is an inside exponent for the log, will come down. So this is the e to the x log of b. So that defines our exponential base b. So for example here, if we want to define pi to the square root of 2, the pi is our base, and the root 2 is our exponent x. So we would define this as e to the x ln b, so root 2 natural log of pi. So we define that in terms of the natural logarithm and the natural exponential, which we had already defined. And then our laws of exponents here will work for our general exponentials, b to the x, because they're defined by e to the x. And then here's what the graphs look like. So if your base is greater than 1, like 2 to the x, then y equals b to the x will go up from left to right. So this would be, for example, like y equals 2 to the x. If your base is between 0 and 1, it'll go down from left to right. So as x increases, it decreases. So this would be like y equal 1/2 to the x, which is actually the same as 1/2 is 2 to the negative 1, and that gets an x power, and then power to a power, negative 1 times x, this is 2 to the negative x. So those are equivalent. So positive base to the x, it increases, and positive base with greater than 1. Positive base less than 1 decreases as x increases, or positive base with a negative exponent. And then just to give us a little bit more intuition, here I have graphed some exponential functions. This one is y equal 2 to the x. This one over here is y equal 1/2 to the x. And notice that those guys are reflections over the y-axis. Okay, and that always happens with 2, 1/2, 3, 1/3, etc. And then this one right here is y equal 3 to the x. So notice for positive x values, it goes up faster than 2 to the x, and that makes sense because you're taking powers on a bigger number. For values less than 0, it goes down lower than 2 to the x because you've got a bigger negative power, so bigger in the denominator. And this down here is y equal 1 to the x, which is just 1. That's a horizontal line. So base is bigger than 1 increases, base is less than 1 decreases. And then here we've got the parabola y equal x squared right there. And then this is the exponential y equal 2 to the x. And exponentials here always grow faster than power. So notice it. The exponential here is below here, but then it passes up the power function. Exponentials always grow faster than power functions. And then this one right here, that's not 3 to the x, that's actually y equals x to the x, sort of a super exponential. With powers, your variables in the base. With exponentials, normal exponentials, your variables in the exponent. With this sort of super exponential, you got both the base and the exponent growing. And we like to use this notation. This is an actual notation. X squared is much less than, eventually, 2 to the x, or any exponential. So I actually could actually do any power here and any exponential. So I could do x to the n and b to the x. So eventually any exponential will be much bigger than any power, and any exponential eventually will be much smaller than this super exponential x to the x. And then logs grow the slowest. So if you've got a log base b of x, that is going to grow much slower than powers do. And the log base b of x is just the inverse of this one, b to the x. So they're reflections over the y equal x. So, and this is an actual notation. It means, much less than. So it's just trying to say that the function on the right, it not only grows faster than the function on the left, it grows a lot faster. So order of magnitudes faster. So this idea will help us out later in the chapter when we look at these races to infinity. So x to the x, that's your fastest growing function that we'll consider at least.